Alright, so today we're going to talk about the iterative method. That is the, one second, to say is we're going to talk about the iteration method and Newton Raphson, Raphson method to approximate x value for a function fx. So you can approximate the root value using these two methods. Right, so we'll start off. So it goes by for the iteration method, it says that if you have a function of fx, that express some sort of x if a function of fx, and you let it equals to 0. So you assume that it has a root, or at least it has a root. So that is your assumption. So that's what you assume. And for that, you can express the form into x equals to another function of fx. Let's not use fx. So you can express it into x equals to, let's say, gx, where gx is, of course, another function of x, and the gx is actually some sort of, it can either be a product of some terms of x, or it can either be a division or some term of x here, or either it could be just plus x. It can be as simple as that. Okay, it could be anything, but we don't care because we know that fx for sure is a function of x, and we know that if it is divided, it is plus, or it is multiplied by any sort of x, then it is also a function of x, and in this case we call it gx. So we call it gx in this case, and from this form, what you can do is you can let x of n plus 1 is equals to g of xn. So what you are doing here is let's say if you approximate a value, let's say xn, let's say it's some sort of value, let's say 1. So you would get xn plus 1, which is x2. Let's say this is x1. Let's say this is x1. And you find x2, let's say you find 1.5. So the theory is, as this go on and go on, if the number converges, let's say if it moves closer and closer, if it converge, so let's write it down, if the number converge, okay? So if the number converge, then the number is the root. Then if the number converge, then the number, let's say if it converges as 3, so x of 3 would equal to the root if the number converge. So 1.5, let's say if it converges to 1.5, then 1.5 is the root. So what is the theorem here is, so if I, according to what I just explained now, I say x is gx, where gx is a function of x, in which it can be either a product of fx with another term, it can be a division, and it can be a plus or minus, it can be anything. But what the theorem here is, if you at the root, we know for sure for a function, at the root, for sure the y term is 0. The y is 0. So the y is actually representing what here is actually, it is representing fx, right? Because we say that fx is a function of x, and we represent y equals to fx. So at the root, the fx would be 0. So this won't matter. So the only way that you could make x equals to gx is if the left side equals to the right side, which is x equals to x. So that is why when it converges to a number, as you go down, you would get the number back. So if it converge, you will get closer and closer to the number. I'll show another graphical example later, but this is basically what it wants to say. So let's erase all the thing. Let me write it down. So we erase all the things. Right. So we write it down. So it says, it says it says if the number converges, let's say xn plus 1 is equals to g of xn until x of n plus 1 is equals to xn, then x of n and equals to x of n plus 1 equals to the root. So this is what the iteration method wants to say. So actually this it has a limitation. So the limitation is the g of prime x n, the size or the absolute value must be less than 1. So the size, the absolute value must be less than 1. So if the g prime is the derivative, the first derivative, and then you put the xn in, if it is greater than 1, by means that it won't converge, it will diverge, okay? The function would diverge, and it won't converge to a value, so you cannot obtain the root. So that's quite a good way to show, actually there's a way to derive the formula, but there's quite a good way to show this thing is true by drawing a graph. So, okay, we will draw a graph. So, let's say this. So, we define x as gx. I don't know what is gx, but it doesn't matter. So, if I know that for sure, if I plot these two in a graph, I would write y equals to x, and I would write y equals to gx for sure. Isn't it? I would write it like this. So, I would have a straight line. Let's have my ruler. If I could rotate it. How do I rotate it? Alright, I rotate it like this. So if I have, say, if I have a y equals to x line, so it would go like this. Say this is, so go away. This is y equals to x. So this is y equals to x. So y equals to gx. So let's say, what if the g prime xn, let's say it is less than 1 and greater than 0. What would happen is, because we know for sure that dy dx, we know that for sure the dy dx for this term is equals to 1. We know that for sure this steep is equals to 1. So the only way for g prime x, the slope, to be less than 1 and greater than 0, that means that it needs to be less than this curve. So one way is I can just take a random. Let's say if I take the g prime x is 0.5. Let's say I take the g prime x is 0.5. That is, it's still lower. So the way you can draw it, it is lower. So if you draw it less steep, you're gonna draw the graph like this. You're gonna draw it like this. You're gonna draw it like this. So this is less steep because the slope is smaller. The slope is definitely smaller. So this is g-axis is not g prime x. This is gx. Let's say gx is a straight line. So, and the g prime x is smaller than 1 and is greater than 0. So what you are doing when you are taking the iterative method is, the iteration method is you are taking one x, you're putting it in, and then you set the x again. You set the x again inside to be the output. The output here is y for sure, isn't it? The output here is y, isn't it? So you put in an input, and then you gain the output, and then you put the output back inside, and then you gain another output, and then you repeat. And then the output here in a graphical presentation, the output is, the output is for sure, the output is y, isn't it? So we can plot it. So if let's say if I take an input here, I say xn, this is xn. This is the thing we need to find, isn't it? Because two lines cross, if two lines cross, we gain the root, isn't it? So this is what we want to find. Say this is x of naught, and this I do x1, I take x of 1. So I put the input, and I take the y value, I take the y value as my output, isn't it? I take the y value as my output. So this here, I know where's my y. So because y equals to x, then I know that for my y, it will correspond towards an x at this point, isn't it? The x would be at this point, isn't it? The x would be at this point, because this is y, this is x, and the x would correspond at this point. If this is y, then x must be here. So you can actually draw for like this, and this is on the line of gx, so you want to refer back to the gx. So you got the output. I know the output is for sure at this point, and I put the output in as an input back. I try to seek another output. So this is the second y. So what if you repeat, you are going to see that you are going to climb this ladder until you reach this point. So this proves that the iteration method, the barrier, is actually correct. You must obey this thing. And same goes with this side. It would just be the same. Okay. So if you take this, you're going to have this, and then this would coincide. Oops, sorry. You should take this because this is gx. Gx is on the bottom. And then you're going to gain this, and then you're going to go like this. Just going to go like this. So until you reach this point, which is x naught. Okay. So it is correct. So I will show you one more. I'll show you the for the cases that it is greater than 1, but I won't show the absolute value. I won't show it, but it is true. You can try. It is indeed true. Oh, let's say if we have a function. Say if we draw out the So say if we draw out the graph. So if we draw out the graph. Oh, this is y equals to x. Oops, sorry, I should use a ruler. Okay, alright, let's say you have something like this, where this should be y equals to x. This should be gx, where the g prime x, where the g prime x, it is greater than 1. Let's say because it is more steep, it's steeper than y equals to x, right? It is steeper. So now we try to do the input and output method again. So if I try to take an input here, remember this is the root that you want to find. So if we try to take an input, we would get this. We would see that the output would lies here. So if we need to take another out, and we need to take, let's say this is this thing, it coincides here. So this is the output, isn't it? So if I try to take the output as an input again, I would get here, and then I would get the next output. It would be right here. So you see this going down the ladder. So it diverges. We say that the sequence diverge, or we say that it does not converge. We say that the x does not converge to a value in which we want to find. So it does not converge, isn't it? But for this, it diverge, and for this it converge, because it converged to one point where that point is the answer we want, isn't it? This is converging, and this is diverging. So same goes with here. If you try to take it, and you're gonna get this as an output, and I take this as an input, you get this as an output. See, it is going up the ladder. So this proves that this is indeed correct. So the barrier is indeed correct, which is this. This is indeed correct, the barrier. Alright, so we'll move on to the Newton's Raphson method. Alright, so we're back. So this is the formula for Newton-Raphson's method. So for Newton-Raphson's method, it states that the x of n is equal, the x of n plus 1, that is the output is equals to x of n minus f of x of n. The condition state should be a function fx is equals to 0. You should express the form is in this. Then you take x of n, an approximate value, and you have f prime of n. Okay, so this is actually, you can try to imagine it in your mind. Oh, we use minus here. So let's say if you have a function going like this, let's say your function graph to something like your function graph to something like this. A function graph to something like this. Let's say it is this thing. So let's say this is y lah. This is y. This is x. So for f prime, for here it is positive. It is positive because it is increasing. It's increasing, and then you are lying on the on top of the y. So this would be positive. This would be positive. And then your x input should take something somewhere around here. Oh, your x is greater than the root. X is greater than the root. And then when you take this, you're gonna minus by some kind of vector, some kind of number, so that you would converge until you converge to this point. So this is what it is doing. And don't worry, because at this point, f of xn would equals to 0, because this is y, isn't it? Y equals to fx equals to 0. At this point, it would equals to 0, so x of n would lie on f of x of n. So it would converge to a somewhat of a number, and you can know. And of course, you have barrier. You have a barrier for this. So the barrier is actually derived from what we usually say, the g prime of x from the iteration method must be less than 1. This is what we say just now. And then you have this thing. So this thing can be expressed as gx. If you can't see it, you can write it down from the iteration method. It says that the x of n plus 1 is equals to the f of, sorry, not the f, the g, a function of x, the g of x of n. So if you compare to these two, you're going to find that this is equals to this, the g of xn is equals to this. So by means that if you take the derivative with respect to x, of course, with respect to x, you take the derivative of this thing, you take the derivative of this part, which is x of n minus f x of n over f prime x of n. Sorry, this should be minus. And then you take the absolute value, it should be less than 1. And you can try to do this. This is very easy. You will get 1 here because x is x, and then you take the derivative, you get 1 minus. This is just a simple quotient rule. This is just a simple quotient rule. This is f prime. Or you take the f prime up. You take the f prime up. You get the f prime, and you take the first derivative of this, which is also f prime. They are the same. And you put a minus, and then you need to take the derivative. So this f prime would be f double prime. You take the derivative, and then you get f over f of prime squared. Take the absolute value. It should be less than 1. And then if you see, this is f prime squared. This is also f prime squared. So you can take this 1. You can simplify this into a single fraction, and you can see that this and this would cancel out. And then of course this will distribute. So you would get the absolute value of f double prime over f is, and then over f of f prime squared is less than 1. And we know that for sure we can distribute this here because it's absolute. Absolute value means that it's positive. And then when you are distributing the positive, you don't need to change the inequality. So what you can do is you would get this f of double prime x of n times the f of x of n, its absolute value must be less than the absolute value of f of prime x of n for the method to converge, for the x number to converge. This is the condition. Okay, this is the condition. Okay, so I'll rewrite it. Give me 1 second. Alright, so this is the final note. So for the Newton's Raphson method, you would have the x of n plus 1, which is some sort of number that you are trying to find, which you are trying to converge into a root, and we call it xn plus 1 is equal to the xn minus the function itself, where the function fx is equals to 0. You express the function in this form, and then you take the x of n and the over the f prime of x of n, and then this is the barrier. So if you want to test whether the number you would converge, your series would converge to a number you just substitute it into this test. So if it passed this test, by means that the number you choose would converge to the root that you are trying to find. Okay, so this is a really useful method to estimate some of the values that we could not easily obtain and we could not easily graph out. So this is quite a good method to find roots for, especially including functions such as e of x. Okay, let's say if you have 10 of x minus e of x is equals to 0. So this is a good way that you could compute and find the roots. Okay, this is a good way that you can find, because if you do it the traditional way, you get 10x equals to e of x. You try to find a root, this would be very hard to find because you would put the ln inside, then you would realize that you can never solve this using an easy way. So it is a good way to use it to approximate the value of the answer. Okay,